So is it visible now?
No, sir, not at getting.
Oh, is it?
Sir, first you open that presentation, then come to the Teams, then share that presentation. First you open, sir, then come to the Teams.
Yes, ma'am. I opened.
After opening that presentation, then come to the Teams screen, then share that one. If you give the share option, you can see that opened document.
Yes. No, I know that I am using it daily in my class. That is not issue. Actually, yeah.
Sir, good morning, sir. First, you open your PPT, sir.
I opened, sir. I opened.
Then share option, sir.
Yes, I share.
Desktop is visible to you, sir. Desktop.
Okay.
Click it, sir.
Desktop. Okay.
Desktop. And select the desktop, sir. And share.
Desktop. Okay.
Okay, sir. If any difficulty, just send your PPT to you, sir.
Already I sent, sir. Already I sent to Sarvan, sir.
Sanjil sir, it's 1 minute, sir. We will take care of them, sir.
Once again, I'll try it, sir.
Okay, you try them. Otherwise, we try them, so no problem.
Okay.
What's up? Sir, Sandil sir.
Yes, sir.
Sir, first open பண்ணங்களா? It's having this document is open.
Yes, sir. Open, sir. Actually, I'm opening in the Google Chrome. 2 times I tried. The Chrome also there is option, and I have opened the PPT also.
Okay, sir. The share option is that the video, audio.
Yes, sir. I know that. Actually, I know that daily I'm using it. The same app I'm using for class.
Okay. Very good.
I know how to use it, but I don't know if there is a technical problem in this.
Yes.
One second.
Sir, 1 minute, sir. We are taking care of this PowerPoint. No problem.
One second, sir. I will try. One second. I will log in. One second.
Otherwise,
Log
we
in.
will take care of your PowerPoint. No problem. We are
Okay, sir. If it is failed, then
them. Otherwise, we will share. We are also doing the work only. PDF, sir. A PDF, it's kind.
No, if you want, I will send PPT also.
Yes, if possible to send this mail ID you send to them, sir.
Okay, sir. Okay, sir.
It's open, huh?
Now it's open, sir.
Okay, sir. Wait, sir.
Now it's open, sir.
It's open, huh? Okay, sir.
The problem is, sir, I entered before the last session itself. So at that time I was entered as a guest. Okay. Now later I have got the enable of the presenter.
Okay. Thank you, sir.
It may be a problem.
Okay. Premila, madam.
My voice is audible, sir.
Yes, sir. Your voice is very audible, sir. It's no problem, sir. Very nice, sir. It's very clear also.
Okay.
We'll start the session, sir.
Yes, sir. Sir.
Okay. 1 minute, sir. It's welcome, Sendil Kumar, sir. Dr. Premila, madam, please introduce our resource person, Sendil Kumar, sir.
Okay, sir. Is my voice audible, sir?
Yes, madam. It's your voice is audible and clear also.
Thank you, sir. Dear participants, good morning to you all, and thanks a lot for your high-level patience. It is a great privilege to me to introduce Dr. M. Senthil Kumar, the speaker of this session. Dr. M. Senthil Kumar received his BE degree in Electrical and Electronics Engineering and ME degree in Power System from Anna University. He received the PhD degree in Electrical and Electronics Engineering from the NIT Tiruchirappalli. His research works has been published in peer-reviewed journals IEEE Transaction on Power Delivery, IET Generation, Transmission and Distribution, and Electric Power Components and Systems. He also worked in the power industry for 5 years as an engineer in India as well as abroad. He received the POSOCO Power System 2018 award from POSOCO and FITT IIT Delhi for his PhD research work. His research interests include power system protection, application of signal processing technique, artificial intelligence technique in the power system. We welcome you, sir. Now I request Dr. Senthil Kumar, sir, to give a presentation on signal processing techniques in smart grid and renewable energy conversion. Thank you, sir. Sir, you please start your session, sir.
Thank you, ma'am. Good morning. So today I'm going to give the lecture on signal processing techniques in smart grid and renewable energy conversion. So my presentation contains this topic: introduction, Fourier transform, short time Fourier transform, wavelet transformation techniques, and application of these transformation techniques in electrical engineering. So we know that the role of electrical engineering in this world, it transfers the energy from one location to another location efficiently, economically, and reliably, right? So it transfers the energy from a remote end. For example, generation station will be located at far end from the load center. Usually the load center will be highly dense in the city area, that is urban area. So we need to transmit the power from remote location to the load center through the transmission line. To increase the reliability, too many generating stations will be interconnected and share the powers, right? So that increases the complexity. When fault occurs in a particular place, any one place, that may disturb the entire system and lead the instability problem in the system. So it has studied about the stability problem in the power system using the equilibrium criterion, right? So when fault occurs the systems, it may have some peak values initially like this, the shown in the figure like this. So initially it may have some peaks and finally settle down the steady state value. The waveform may be distorted one. So the objective of the protection system is come to the objective of the protection system is to isolate the faulty section as soon as possible, right? You should act very quickly so that we can clear the fault within the critical fault angle. So we have studied in the power system critical, what do you mean by critical angle or time. So there is a criteria. If you clear the fault within the critical angle time or angle, you can ensure the stability of the system. If a fault could not clear within the time, then it may lead out of synchronization of the whole system. So that may lead out of outage in the whole system outage, right? So when we have the fault current like this, the relay has to detect and act effectively. So this is the biggest challenge for the protection systems. So when you have the distorted waveform, so that will highly affect the measurement as well as protection systems. So here we have the role of signal processing techniques. So the signal processing technique will eliminate all the higher order terms. So a disturbance other than the fault will eliminate the signals which is related to other than faults and will detect only the fault related waveform, that is fundamental components and estimates. So that which helps to make the perfect decision and will isolate the faulty section, right? So it is very similar to like passing the light through prism. So you know that prism, when you pass the light, that will split the light into the different colors, right, in this different color spectrum. So the same way, when you apply these transformation techniques, so signal can be analyzed in better way. So it may give the information about frequency component exists in the signal. So that will help to improve the power system protection and power quality, smart grid, so and more application RTDS. So before start the signal processing application, I like to give brief introduction on what is the signal processing techniques and the basics of signal. So let us start from here. The signal, any physical quantity that varies from the time, space, or other independent variable will be called a signal, right? If it is electrical engineering, we can say that the voltage and current, these are the two parameters we can fetch from the power system, can be used for the further measurement or to make the control or production operations, right? So this is this will be used as a signal, right? Current and voltage signals. The first one, you can see that the figure, it is a highly distorted the voltage waveform. So the dotted lines is another waveform. So we can use some signal processing technique to estimate the harmonics common accumulated in the signal. The other one example, it is just used in the medical, that is ECG signals to see the performance of, that is know the condition of your heart perform. Okay, the most of the signals are real time in the real time or analog in nature. This is a function of continuous variable. So we'll be using the analog processing systems, that is processor. So it will be made by the op-amp or transistor circuits. This was used in olden days. So input analog will be given and it will process, finally will give the analog output signal. However, the digital signal processing offers several advantages than the analog signal processing, such as flexibility to change in signal processing operation by software. So if you want to change the function, so you can modify easily by changing the codes. So once your data is available in the digital form, you can play with it, right? That's the flexibility. And it offers better control of accuracy requirement. So accuracy can be increased with help of increasing the sampling frequency as well as the number of bits in the digital representation. So that will increase the accuracy and allows for implementation of more sophisticated signal processing algorithm. So if you want to examine new kind of algorithm, then redesign is very simple. No need to go for hardware redesign. So you need to modify only the program. So it will be easy for implementation. Adaptability over wide range of applications. So it can adapt for any kind of applications. For example, if you are using some kind of application, so for example, we are using for signal processing tool for protection system. If you want to apply for some other harmonic estimation, so only small things we need to modify in the hardware side, then you can reuse it, right? This is the adaptability, the property of adaptability. Also, it has some limitation, that is speed of operation ADC. There is a limitation in the ADC operation. It will be limited by megahertz. So there is the limitation and is costly. So when you want to high accuracy, then obviously you should go for high sampling frequency. Then it will be limited by cost. Right. So what is the signal processing? So usually we have the real-time signal as an analog signal that should be converted into. First, it should be converted into digital signal using ADC. So then the digital signal will be given to digital signal processor. So where we can perform filtering, transmission techniques, or some other application related with the processing, right? Usually they will be using filtering and transmission techniques. Especially in electrical engineering, we will be using transmission techniques to estimate the fundamental and the other harmonics which is related to our control and protection techniques. So, and the output part, in the output part of the signal processing unit will be in digital form. So that will be converted into analog form using the digital to analog converter. So some application you can give the digital signal directly to the output mode. For example, you may have some printer or display. That the case, then you can give the digital signal to this output actuators. So some cases you may have the actuators, then you should give the analog signal. So the particular application you need to use DAC. Mostly. So now let us see what it means by analog to digital conversion. So ADC has 3 steps of processes such as sampling, quantizing, and encoding. Sampling, which converts the continuous signal into discrete time signals. So for let us consider the one example, x of a of t, xa of t. So this is an analog signal. So it can be sampled with periodic interval of t, then it can be represented as x of nt. So which can be written as x of n. So once it's converted to instant sampled instant value, then it can be called as x of n. So the next one is the quantization. Quantization, so it converts, actually we can say that the mapping the discrete sampled value into discrete final value. So what do you mean by discrete finite value? So the number of finite values depends upon how many number of bits used in the digital representation. So for example, we have the 4 bit. If we want to represent the -8 to say +8 volt. For analog signal, it will be varying from -8 to +8 volt. So we have the range of 16 volt, right? 0 to 16 volt we need to represent with the help of 4 bits. So 4 bit can represent 16 stage like this, 16 stage. So it can start from the -16, the 0 corresponding to -16, the 15 state corresponding to the +16. So if you have the in between voltage, the sampled voltage may be, for example, 8.3, 8.1. So that will be mapped into the finite value. Finite value is so 8, 7, 6, 5 like this. These are the finite values. So mapping will be done with help of the quantizations. The final one is encoding. that is represent the discrete finite value by the p number of sequences with sequences. So this is what analog to digital conversion. So the next one is sampling criteria. This is the most important factor to need to consider while doing the ADC conversion, that is analog to digital conversion. The Nyquist sampling theorem states that sampling frequency should be at least twice the highest frequency contained in the signal to avoid the aliasing. So let us see what do you mean by aliasing. So let us consider one example. Here we are going to sample the 50 Hz signal. Then your sampling frequency should be greater than or equal to 2 times of the 50 Hz, that is 100 Hz. So you can go ahead more than 100 Hz, right? So this is what criteria is given here. Say f of s should be greater than or equal to 2 times of the maximum frequency available in the signal. So now we have 50 Hz signal. So sampling frequency should be 100 Hz. Means that we have 2 samples per cycle of 50 Hz. So if we use 100 Hz as a sampling frequency, right? So for better accuracy, we should go for higher sampling, right? Is the minimum criteria. So for better accuracy, we should for higher sampling. So here I have considered 400 Hz. So if it is 400 Hz, then number of samples for 50 Hz per cycle will be equal to 8. So now we have 8 samples. So 1, 2, up to this one, 8 samples. We have 8 samples, right? Now we are going to see one more example how we are going to get aliasing effect if you have the violation of the sampling criteria. So let us consider one more example, 350 Hz. Okay, 350 Hz sinusoidal waveform. Now I am going to sample with the same sampling frequency what you consider here, that is 400 Hz. So 400 Hz is greater than 350 Hz. 350. So minimum criteria is 700 Hz. But what I am going to use is 400 Hz. So if I use the same sample instant, so I'll have the sample instant at this location and here like this, right? So if you plot it, so the final output voltage will be like this. Sorry for inconvenience, actually it's misaligned. It should be like this. It should be like this. There is a misalignment in the waveform. Sorry for your inconvenience. Consider this after sampling. So we'll have the waveform like this. If you reconnect, for example, if you reconstruct the signal into the analog using this sampled value, so you'll get the analog signal like this. So it may confuse us, right? So there is no difference between 50 Hz and 350 Hz. That's what called as sampling. Sampling, that's what called as aliasing. So aliasing is, so you cannot distinguish between two different signal if you violate the sampling criteria. Right. So now let us get into the transformation techniques. So what do you mean by transformation techniques? Why we need transformation techniques? The time domain signals is represented, usually the time is represented by time amplitude plot, right? Which does not reveal any information explicitly. For example, ECG. Only doctors can read the ECG signals, then he can tell information about the patient conditions, right? So nowadays, in abroad, they are using the Fourier spectrum analysis of ECG signal, which give the information about the frequency content. So which gives some nice information about the frequency contents. So with the help of this, so even the common man can interpret something the patient conditions. So this is what is the practice now in abroad. So this is one of the application in the medical side. So as far as electrical concern, so let us consider this is a waveform, that is a signal. So this look like a sinusoidal. It has some harmonics component. You can see that. So if you apply the Fourier transform, so you'll get the result as 10 times of the fundamental harmonics, 2 times of third harmonics, 0.5 times of fifth harmonics and 1 times of the seventh harmonics. So sum of these components it looks like this signal, the example signal. So it's actually is not a pure sinusoidal voltage, so it has some harmonics now. So this, the transformation techniques will give the clear picture of actual signal. So it will be giving the information regarding the actual signal, so we can estimate, then we can go for the filtering, that is harmonics filtering. So based on the estimation we can go for filtering. So transformation techniques represent any signal by sum of finite function. It may be a function, may be a sinusoidal function or any other functions, right? So it's like very similar to passing the light in the prism. So Fourier transform techniques, it's a familiar one which is used in the electrical engineering. The Fourier transform decomposes the signal into sum of sinusoidal components, sum of harmonics. So the same example what we considered previous one. So what's the advantage of the Fourier transform? Since we are using the sinusoidal function in the Fourier transform techniques, it's offer great advantage in LTI system. LTI means that linear time independent system. So if you apply the sum of the linear sum of sinusoidal function at the input, the LTI system produce the linear sum of sinusoidal function at output, but it may differ in the amplitude and phasor, but function remains same. So you can see that the frequency of the first current will be remain same, but there is a change in the amplitude and phasor. So we can represent the same function in the output, but there is a change only in the amplitude and the phase angle. So this is the greatest advantage with the Fourier transform. That's why it's got popular in the electrical engineering, since most of the system in the electrical engineering will be more or less LTI system. So there are two types of Fourier transformation techniques. One is Fourier series and the one is Fourier transform. The first one is Fourier series will be applied for periodical signal. So it's what is going to give? It's going to give linear weighted sum of the sinusoidal function. Any waveform, any function can be represented sum of weighted sinusoidal function. This is the equations. Is a familiar one. The C of k, which is equal to 1 by TB, summation of TB. So this integration of TB. So I have to multiply x of t, this analyzing signal, with the Euler function. So exponential frequency component. It has a cos frequency component and the index f naught is the fundamental frequency. So t is the time. So you can integrate for the particular period where we have the periodic property, then we can apply the division so that we'll get the magnitude of the particular signal. So let us consider one periodic signal. It's a pulse signal. It's a periodic signal. If you apply the Fourier series, you'll get the Fourier spectrum corresponding to the frequency 0, F, 2F, 3F, 4F, 5. So F represents the fundamental harmonics. It depends upon your assumption. F naught can be 50 hertz, whatever your assumption. You can consider any frequency. Then based on the F naught, then you can have the multiplication of the fundamental frequency spectrums, right? So one thing you should note here. So the spectrum is in discrete form, right? So you have the equal distance between each frequency. Okay, right. So this is this is what Fourier series. Fourier series will be applied for periodic signal. So come to the Fourier transform. So Fourier transform can be applied for aperiodic signal, that is non-periodic signal. So how we can apply the aperiodic signal? So earlier we have applied Fourier series. Same thing we are going to apply. See, additionally we are going to assume one thing, that is the periodicity. Periodicity will exist for infinity period. So minus infinity to plus infinity. The periodicity extended for minus infinity to plus infinity. So that's what we have mentioned here. The TP tends to infinity. That is periodicity period tends to infinity. So if stretch this window, then it can be called as Fourier transform. Then we are assuming that within this will be periodicity will be maintained, repetition. So Fourier transform of continuous signal. So the same formula, almost we have the same formula, x of t e power minus j2 pi ft, right? So we are going to integrate minus infinity to plus infinity. In the early case, we have integrated from 0 to tp, that particular period. So we are going to integrate. Additionally, in the previous equation, we had the division, right? After doing the summation, we need to divide. Here we cannot divide since we are going to integrate for the infinity to minus infinity. So division will not be applied here. Here you can see that the frequency spectrum will be in continuous function. It is in continuous function. So earlier it was in discrete, right? It will be continuous function. So this is a discrete Fourier transform. So I have the two versions. One is Fourier series and Fourier transform. This is a discrete version of what we discussed earlier. The same thing. Okay, same formula we are going to use in discrete form, right? But you need to consider that digital computer cannot apply for minus infinity to plus infinity. So in it there is a limitation. You can apply only for finite length. So it will be applied for finite length. So this will be replaced from 0 to minus n minus 1. 0 to n minus 1. So there will be limitation. So in real-time application, we will be using discrete Fourier transform, the computer or real-time applications, simulations, all those things. Now, I like to give the illustration of the Fourier transform. What's happening inside the Fourier transform? So it may give the better understanding of Fourier transform. So we don't know the frequency of the consider this analyzing signal. So now what we are going to do? We are going to estimate the frequency component exists in the analyzing signal. So what we have to do? So we have to apply this formula. First, you have to multiply the analyzing signal with Euler function, that is exponential frequency component, right? Exponential frequency function that should be multiplied with analyzing signal. Finally, have to sum up, right? All instance should be summed up for n to n minus 1. Sorry, 0 to n minus 1. Okay, so this is what we have to do. First, e power j omega n can be divided as cos and sine function. For better understanding, I represent the time continuous function, cos 2 pi 50 into t, sine 2 pi 50 into t. So here we are going to multiply. First we need to multiply the cos term and we multiply with sine term. So resultant will be like this. So this purple color represents the multiplication of cos and analysis signal. The green color represents the multiplication of sine and the analysis signal. Right. So now what we have to do after multiplication? We have to perform the summation. So now we are going to perform the summation. If you sum up all the instant in the signal, what's the result? So see here, the signal is bipolar. So when you apply the summation, bipolar, the result of the summation of bipolar will be equal to 0. So you have equal positive and negative waveform, right? So come to this, this one, result of sine multiplication. So here we have the only positive side. We have only positive side. So if you apply summation, so if you perform the summation, so you will have the final result. So now let us examine another frequency. The same frequency I have considered. We have to check with the next frequency, 100 Hz, the second harmonics. So we have to apply the multiplication. So this is what result. In both cases, we have the equal positive and negative half cycles, right? So what will happen? The summation will be equal to 0. Similarly, if you consider 50 Hz, if you are going for analyzing third harmonics, the summation will be equal to 0. So the resultant will be 0. So what we can interpret from this one? So when your frequency component, the Euler frequency component matches with the analyzing frequency component, then there will be coincide, then it has some finite value. The summation will have some finite value. When you multiply with some other signal, so we will get 0 value. So this is what we need to interpret from the Fourier transform. Then in the MATLAB simulation or any real-time application, you would have heard the FFT instead of DFT. You would have heard this word often: fast Fourier transform. Fast Fourier transform is not a technique, transformation technique. It is an algorithm to compute the DFT efficiently. So FFT uses the symmetry and periodicity property of DFT to reduce the computation burden. It reduces the computation burden from n squared number of operation to n into log n number of operation. For example, if you have the n equal to 1024, then direct DFT calculation takes 10,48,576 operation. If it is FFT, the same for same operation, so we need only 7,097 operation. So there are several among the FFT. There are several FFT algorithms to evaluate the DFT efficiently. Though the radix 2 algorithm is most popular algorithm. FFT is widely used in electrical engineering as well as mechanical engineering, music, science, medical engineering, etc. So what's the drawback of Fourier transform? So let us consider one example, that is the analyzing signal consists of 4 frequency components. That is sum of 10, 25, 50 and 100 Hertz signals. So the result and the summation of this all frequency will be like this. So if you apply the Fourier transform, we will get the result like this. So it will give the clear picture of what are the frequency components exist in the system of a signal, right? So this kind of signal will be called as stationary signal. Means that the frequency component exists in the signal will be existing whole period from 0 to 500 Hertz. All frequency component exists, right? So the frequency content do not change with respect to time. So other case, non-stationary signals. Let us consider non-stationary signal. It means that the frequency contents change with respect to time. For example, first 300 milliseconds we have 100 Hertz frequency signal. The another 300 milliseconds, 300 to 600 milliseconds, we have 50 Hertz signal. The later 600 to 800 milliseconds, we have 25 Hertz. The last period, 800 to 1000 milliseconds, we have 10 Hertz signals. So this kind of signal will be called as non-stationary signals. If you apply the Fourier transform, we'll get the result like this. So it shows the peak at the same frequency, that is 10 Hertz, 25 Hertz, 50 Hertz and 100 Hertz. But it never gives the information about what time the 100 frequency was available or what time in the 50 Hertz signal exists. Okay, it will give the information about what frequency exists in the period. Will never give the time period, what frequency exists at what time. So that's what drawback of Fourier transform. So we can conclude that the Fourier transform is not suitable for analyzing the non-stationary signal. So come to this short time Fourier transform. To avoid this, eliminate this problem, we are going for short time Fourier transform. So what do you mean short time Fourier transform? So you can see the example, some portion of the signal is stationary, right? The non-stationary signal. So we can say that some portion is a stationary signal. So we can apply the Fourier transform segment wise. So we can get the information at particular time interval. So that will be known as short time Fourier transform. So in order to apply the particular portion segment, we are going to use some windowing function. So additional with the Fourier transform, we are going to use some window function. The same equation what you had in the earlier Fourier transform, x of n and Euler function. Additionally, we are going to have one more function, windowing function. So window. So there will be a window fixed for certain period. So the particular period, the Fourier transform will be applied and the information and the Fourier spectrum will be extracted. That will be stored. Then the window will be shifted next page. So let us see this picture. So we will get a clear idea. So now we have the window. This is located at first 200 milliseconds. Then the window moves to 200 to 400 hertz, 400 milliseconds. Then it's moved to another 200 milliseconds. So window is moving step by step. So still we are applying the Fourier transform, but segment wise. So this known as short time Fourier transform. So the length of the window is a crucial factor. How to fix it? So length of the window is fixed one, right? So we can assume that the length of the window, we assume that length of the window satisfy that where the stationary is exists. So STFT, short time Fourier transform, provide the information of certain band of frequency exists at any given time interval of time interval. It's not give what frequency exists at what time. It not give the particular instant. It give the time interval. Band of frequency exists at time interval. So this is what called as resolution problem. So if you use very narrow window, for example, if you use very narrow window, so we cannot accommodate the high frequency component, right? So since the window is very narrow, so you can accommodate you can accommodate the high frequency component. We cannot accommodate the low frequency component inside this window. So that will give the good time resolution, poor frequency resolution. Since it's a very narrow, we can go for multiple steps in the time axis, so that it will give the good time resolution. However, you can't accommodate the low frequency signal within the window area. So you cannot give the good frequency resolution. So when you use wide window, so we can accommodate all frequency component from low frequency to high frequency, but you cannot move in multiple steps in the time axis. So there is a failure in time resolution. So if you use wide window, that will give the poor time resolution and good frequency resolution. This is the problem associated with the STFT. So if you fix some particular window size, then you may face any one of the problems. So resolution problems. So that can be started using the Wavelet transform. See this Wavelet transform, what you are going to do? We are going to vary the window size with respect to the frequency. What frequency you are going to evaluate? Okay. So it's going to variable. The window size is not fixed one. It's going to vary. Additionally, we are going to use some other function other than the sinusoidal function, some other Wavelet transform. So this is a function. So x of t will be multiplied with some function. So the function will be called as usually mother wavelet. Okay, you can use any kind of different functions are available. Simlet, Harlet, Har wavelet, then deposits. So you can use any kind of things. It depends upon our applications. So the windowing size will be varying with respect to frequency components. So that can be taken by the the scaling factor. So now come to this resolution. How we are obtaining the better resolution in the time frequency plane. So in this plane, you can see that the frequency, this is the frequency in y-axis, x-axis time scale, right? The frequency, when you come to the low frequency, the division in the frequency scale is very narrow. It means that it gives the better resolution in the frequency, in low frequency side. So when come to the higher frequency, the length of this, length of frequency window is greater. So the resolution getting poor, right? When go for high frequency. Okay. So come to this time axis. Now you can see that in the high frequency side we have multiple segments, so that we can have the good time resolutions. Good time resolution. When come to this at the lower frequency side, we have the only one window the whole period. So we are getting poor time resolution. However, the beauty of Wavelet transform is it meet out the Heisenberg inequality constraint. That is, the area of the box, each box will be equal. Whatever the resolution, the area of each box. See here, this is the length. The length of this window is higher than other remaining boxes. However, the height is very less, right? So when you compare the all area of boxes will be equal. So it can maintain the resolution. Okay, maintain the resolution in better way. So when you go for high frequency, we'll have the better time resolution and poor frequency resolution. When come for low frequency side, so we'll have the better frequency resolution, poor time resolution. Okay. So another one is discrete wavelet transform. The discrete wavelet transform is not exactly discrete version of the continuous wavelet transform. It is developed with subband coding. It's like passing the signal through set of high pass and low pass filter. So for example, if you have the signal of x of n is contained the frequency from 0 to 1000 hertz. Obviously the sampling frequency should be 2000 hertz. Then it passed to the high pass and low pass filter. So high pass filter will give the result of 500 to 1000 hertz. So this will be called as level 1 detailed coefficients. Level 1 detailed coefficient. Then the low pass filter gives the information of 0 to 500 hertz. This signal again will apply to set of high pass low pass filter. Then we'll have the level 2 detailed coefficient which contain the 250 hertz to 500 hertz signal. The other low pass filter in the second stage will give the signal of 0 to 250 hertz signal. So again, this low pass filter frequency component will be applied a set of low pass and high pass values. So you can apply if you want to decompose further level, you can apply further decompositions using the high pass and low pass filters. So it is according to a requirement in the applications. So now the result will be like this. These are the result will be available from the discrete wavelet transform. So detail coefficient 1 which contain the information of 500 hertz to 1000 hertz. Level 2 detail coefficient will contain the information of 250 hertz to 500 hertz. Level 3 detail coefficient has the information of 125 hertz to 250 hertz and approximation coefficient of 0 to 125 hertz. So it will not give the particular frequency. It will give the band of frequency available in the particular period. So other than the wavelet transform, we have Hilbert S transform, random transform, so which can be applied for electrical engineering, depends on the application. So it depends on each transformation technique has own advantage and disadvantage. According to advantage and disadvantage, we can determine the applications. So now let's get into this application. The first application is transmission line protections. So in the introduction part, we had discussed about how what's the role of protection system to maintain the stability of the system. The system may have the subtransient period and transient periods. In the subtransient period, they have the peaky non-sinusoidal waveform. So, but the relay has to estimate the fundamental harmonics and detect the fault, right? So, additionally, the system may have the power swings that may add some challenges. So, when fault occurs, the relay should respond very quickly to isolate the faulty sections. So, most of the disturbance in the power systems occur due to this relay maloperations. So, we should go for better protection system to avoid this disturbances, right? So the fault current and voltages contains DC component, harmonics, other interferences. So from this we need to filter out only the fundamental harmonics using the transmission techniques. So you can use either Fourier transform. The olden days they have used Fourier transform. Now they have introduced the Wavelet transform. So additionally, additional to the Wavelet transform, have applied Hilbert and S transform. Some applications. So it depends on the problem we are considering. We are going to see one by one. Addition to this, we have some more challenges along with remote and feed, power swing, fault resistance, mutual coupling of parallel lines. So these are the challenges given for the transmission line protections. It can be managed with help of this transmission techniques, signal processing technique. So distance relay depends on the precise fundamental quantities, that is going to measure the fundamental components which provide the valuable information for the relay to respond to the fault. Here we are going to see one example. Okay, this picture gives the comparison of discrete Wavelet transform and discrete Fourier transform. So both will be both are used to estimate the fundamental harmonics. When compared with DFT, the DWT Wavelet transform estimate the fundamental harmonics very quickly, so that it can help to isolate the fault quickly, so that we can isolate the faulty section before the critical clearing angle. So let us see the measurement in the impedance relay. So here the figure shows the RX plane of the Moore relay characteristics, which is used for transmission line protection. So here the LG fault is considered with the fault resistance of 15 ohm, right? So here the impedance trajectory is given in the RX plane. This mark shown corresponding to the time. So the round symbol is corresponding to 0.619. Corresponding to 0.7124 second. The cross mark is corresponding to 0.180 seconds. So you can compare this result. At 0.6927, the measured impedance value, see the measured impedance value of TFT, it is far away from the operating region. This is what operating. Inside this circle, we have the operating region. It's far away. But DWT, that is Wavelet transform components, very closer. So when compare with, let us compare at time 0.1724 seconds. So this is very close to this operating regions. So see that another time period. So DFT is reaching this, entering in the operating region later than the DWT, that is Wavelet transform. So the Wavelet transform can help to estimate the fundamental harmonics effectively and fast, very quickly, so that we can operate the relay quickly, isolate the faulty sections. Let us see one more challenge, that is power swing. What is the power swing? So power swing, when system oscillates due to fault occur in some other line. For example, we have the relay for particular bus, but fault due to the fault occur in some other system line, the voltage angle is going to oscillate. The generator voltage is going to oscillate with respect to the reference bus, right? So that will give the oscillation between the two bus voltages and currents. See there, you can see the oscillation. How is it? So there is a fault, okay, at some other line which is occurred at 0.6. It's occurred at 0.6 and cleared at 0.7. The fault is clear. Even the fault clears, the oscillations, the power system has power oscillation exists, okay, till this period. So this will be called as power swing. So this is current waveform, this is voltage waveform. You can see that current and voltage waveform is oscillating severely. So when you use the impedance relay to measure the impedance using this current and voltage waveform, so the resultant will be like this. The measured impedance is getting down. See, we are getting very low values which enter into the operating region of RX plane. Will enter into operating region of RX plane. So that will create the maloperation. So that can be avoided using the Wavelet transform. The other challenge is when power swing occurs, so we can use some blocking method, power swing blocking method. So we can block the trip due to the power swing. But if fault occurs in the particular line, once again, the particular line during the power swing, then we cannot detect the fault, right? Since we are going to apply the power swing. So these problems can be sorted out using the wavelet transform decomposition. See here, the wavelet decomposition applied for 13 levels. Applied for 13 levels. So we have the D1 to D13. So frequency component, detailed coefficients. So the D1 to D4 frequency, high frequency component will be used to estimate the fault occurrence, and the frequency component corresponding to the fundamental harmonics, that is 50 Hertz, which is occur in the D9 level, right, will be used to estimate the fault. Okay, the D1 to D4 and D9 will be used to estimate the faults. Additionally, the low approximate value and higher order detailed coefficients like a D13, 12 will be used to estimate the power swing. So the power swing will be in terms of 1 to 3 Hertz. 1 to 3 Hertz. So you can see that 1.7 to 2.7 seconds. So 1 second, you can see the window period is 1 second. So how many cycles we have? 3 cycles. So 3, you can say that 3 Hertz. The oscillation will be in 3 Hertz. The power swing oscillation will be 3 Hertz. So that can be estimated effectively using this wavelet, high level wavelet decomposition components, right? So the wavelet transform will be very useful to detect power swing as. So let us see one more example, that is smart grid, how it will be used. The wide area measurement will be enabled by the phasor measurement unit. The phasor measurement unit provide the synchronized phasor value of each buses. Okay, it is synchronized with the GPS clock. So each measurement unit located in the bus bar there is a sorry for interruption, there was a network problem. I am continuing. So the PMU will be synchronized with the GPS clock. So PMU will be giving the time stamping with each instant, that is phasor measurement. So for phasor measurement, we'll be using discrete Fourier transform. Once you estimate the phasor and magnitude, that will be time stamped with the GPS clock. Okay, then we can transmit anywhere the signal, the time stamp signal can be transmitted anywhere. There we can collect the all PMU values with the time stamping. Then we can coordinate in the time corresponding to the GPS clock. So this will be called as synchronized measurement. So not only the phasor and voltage. Additional to this, we can transmit the megawatt, megavar frequency, rate of change of frequency. So the sampling instant will be equal to 50 times per hertz. So 50 times per second, or 2550 for 50 hertz signals. Okay. So nowadays in industry they are using discrete Fourier transform to estimate the phasor and magnitude. So now some research paper have reported with wavelet transform and short time Fourier transform. So we can try some other transformation technique also to give the better results. So if you want to extend this PMU into the protection, so we need to apply some time localization transformation technique like a wavelet transform. So we can apply with the Hilbert transform, transformation technique. So that can be studied with the PMU. There is a research area. So if you want, you can explore it. So now let us examine another application in the transmission line, differential protection. So the differential protection can be applied for transmission lines also with the help of the fiber optic cable. So the fiber optic cable will transmit the current signal measured at each ends. So it can transmit other end, remote end, so that we can have the comparison of two ends currents at each locations. Then we can apply the differential current algorithm. But the problem associated with the transmission line differential protection is distributed shunt capacitance and delay in the equalization between local and remote current. So what do you mean by that? So the transmission line has the distributed shunt capacitance, right? That will introduce the shunt capacitance current. So that will produce some additional time lag in the current signal. Then the delay in the equalizations. What is mean by equalization? So actually we are going to send the one data. There is a two bus VI, I bus and J bus. So this current signal will be sent to this other node. Similarly, this current signal will be sent to other node. So when you send this IJ current, there is current in the jth bus there. So the fiber optics communication will take some time delay. So that time delay will be accounted, equalized using some components at the remote end, the ith node. So that be varying, did not be constant, that will be varying with respect to operating condition. So this problem can be solved out using the PMU measurement. So the PMU will get the information of current signal and timestamp with the GPS clock that will be transmitted through the fiber optics. So then we can coordinate, we can compare the current signal at two ends corresponding to the GPS current signal time. So additional to that, so the transmission line with fax devices like SVC, TCSC, UPSC, so one of is going to give more challenges for power system protection, since it's going to add some other components inside this transmission line that will confuse the protection device. So it can be managed with help of Wavelet Transform techniques. So Wavelet Transform has been applied to extract the both low and high frequency component of the fault signal to eliminate the impact of non-fault disturbances. So non-fault disturbance is mean that the operation of SVC. So the SVC, TCSC or UPSC, which is incorporated in the transmission line, it may have some impact. It may have some impact in the measurement. So that can be filtered out using the Wavelet Transform techniques. So additionally, the S transform, Hilbert transform have been applied for fault detection, classification, fault location in the fax compensation devices. Now let's move into the differential protection for the power transformer. So the differential protection can be applied for power transformer. Okay, so it will be compare the two currents of primary and secondary current. The real challenge is associated with the interest current. So when you have the interest current that has a significant magnitude, so that will give the significant magnitude that lead the maloperation of the biased differential protections. So to eliminate this action, so we are going to use some transmission techniques. So usually in the interest current occurs when transformer is energized. So it may go up to, the magnitude may go up to 8 to 10 times of rated current. So obviously it's going to lead the maloperation. So second harmonics blocking method used in the conventional relay to prevent the relay operation. So the second harmonics component is estimated by the Fourier transform techniques. So we can estimate the second harmonics ratio, that is ratio between the second harmonics component and fundamental harmonics components. When the second harmonics ratio exceeds certain value, threshold value, so we can conclude that there is a presence of the interest current. So in the relay operation can be blocked. So the Fourier transform used in the conventional relay, however, it has maloperated certain cases where you know that it cannot be applied for non-stationary signals. right? When you have the high transient signals in the power system, that is equal to the non-stationary signal, right? So that will lead the maloperation in the case of Fourier transform. So to avoid this one, wavelet transform and Sipler transform have been applied to handle this non-stationary signals. So other kind of transformation techniques, that is empirical. Empirical means that you can develop according to the requirement. You can develop your own transformation technique according to the requirement. So based on the experience, we can develop. So what is required for you? So we have developed a transformation technique, empirical Fourier transform. So it is discriminating the internal fault and interest current effectively. How? So you see here what is going to, you can see the mathematical equations. So first step is very similar to the Fourier transform, that is multiplying the analyzing signal with Euler function. Then resultant will be divided as a two part. The resultant will be divided as two part. It is given in the picture also, right? Then the result we are going to multiply the first half with second half. Just we are going to multiply. If you have the two things, we have to multiply the first half and the second half. So if you will multiplying this one, if you have the while multiplying this one, if you have the signal of interest current, see the interest current, we have the peak at 1 half cycle, the remaining are almost 0. So while multiplying, the resultant will be 0. So that is the beauty of this transformation techniques. So we have developed based on the experience. So what is the record for our to detect the interest current? Okay. So if it is internal fault, both positive negative. So if when you multiply both positive negative, so you will have the significant amplitude that will be equal to the Fourier transform. So this brown colors is EFT, that is empirical Fourier transform result. The yellow color represents the DFT. So in case of internal fault current, the magnitude estimated using the EFT is very equal to the DFT. In case of interest current, the EFT gives very less component. So it will give the clear picture between the internal fault current and interest current. So this is the advantage with the empirical Fourier transform. So we can understood that how you can use this signal processing tool for electrical engineering. Defined as concept of powering and grounding sensitive equipment in a manner that is suitable for operation of the equipment. So power quality events can be described as defined as voltage sag, swell, interruption, voltage imbalance, impulsive transient, oscillatory transients, harmonic distortion, notching. So you know that what is meant by sag. Sag is the decrement in the voltage level from 0.1 to 0.9. Voltage swell is voltage increment in the voltage level above 1.1 per unit. The interruption is decrement in the voltage level below 0.1 up to 6 minutes. So voltage imbalance, there is a unbalance in the voltage magnitude. The impulsive transients, so unidirectional voltage waveform incorporated in the sinusoidal functions. The oscillatory has a bidirectional signal incorporated accumulated in the sinusoidal functions. Voltage fluctuations, the variation in the RMS value, so that in the narrow band, and harmonic distortions. So when you go for power electronics devices, that will introduce high harmonic distortions. So the harmonic, when you have the harmonics distortion in the system, that will produce the more heat in the machines. What are the machines we are using in the electrical application? So that will produce the more heat, and more heat that will not good for the electrical machine life, right? Another one is notching. Notching is so periodical disturbance occurred in the systems, right? So usually caused by the line commutator power electronic devices. Poor power quality can cause the malfunction of electrical and electronic devices, equipment, instability, and short lifetime. the harmonics can adverse affect operation, cables, capacitor, metering, protective relays. So Fourier transform can be used to estimate the harmonics in the systems. So here there is an example. So this is very similar to the inverter output. So usually we have the inverter, we have the square waveform, right? So if you design the special inverter, it may have the approximate sinusoidal function. Usually we have the square waveform at the inverter output. So it contains high level of harmonics. You can see the spectrum of frequency spectrum of this square waveform. So for first harmonics, third harmonics, fifth and seventh, ninth harmonics, right? So it's the sum of the harmonics will be represented as a square waveform. So addition to this, when you have a non-stationary signal in the power quality issues, we can use the wavelet transform, that is time localization. Not only wavelet transform, Hilbert S transform can be applied to estimate the harmonics effectively. The other application is real-time digital simulation. So which will be used to evaluate any algorithm. It may be related to control techniques or protection techniques. So if you want to test the control techniques, what you develop in the real time, then you should go for hardware in loop testing, HL testing, right? So the RTDS is able to simulate electromagnetic transient phenomena in real time with help of multiple number of DSP, that is digital signal processor in parallel, right? So RTDS is very similar to the MATLAB simulation or PSCAL simulation, whatever it is, whatever the simulations are. But the simulation time is equal to the simulation runtime. The simulation time is equal to simulation runtime. But however, in MATLAB or some other guys, the simulation runtime will not be equal to simulation time. So here the speed is matched with help of the DSP processor. So it can be connected with hardware loop with the some microcontroller where we want to implement your own algorithm. Okay. So you can use some microcontroller or DSP processor. You can implement your algorithm that can be connected in the hardware loop through the analog input and output channels. So sometimes you can use digital input, analog output channels. So the simulation, for example, if you have the power system simulation, if you are performing the power system simulation, the current signal can be routed into the analog output channels that will be given to the ADC of DSP processor. So where we can evaluate the actual analog signal which is received from the RTDS. Then we can evaluate the algorithm that will give the response, right? That will give the response. So that should be fed back to the RTDS through the digital input, right? So if it depends on if it may be a digital input or an analog input, depends on. So again, this input will be given routed to this simulation diagram. So where we want to operate some component in the simulation. So you can evaluate the algorithm in real time using RTDS. So where we have the role of signal processing tool. So thank you for patient listening of this lecture. So if you have any queries, we can discuss now. Saravanan sir, I have completed my part. Yes, sir. Thank you. Thank you, sir. Okay, sir.
So please post in chat box. Otherwise, please unmute your audio and ask the questions. Interact with the resource person. Any participants, any queries? Hello. Friends, if anyone having any queries, unmute your audio and directly interact with our resource persons. Okay, ask for Naresh.
Hello, sir.
Yes, sir. Please.
In pulse modulation technique, actually, aliasing effect will come, sir. Actually, how can we avoiding the aliasing effect? How it forms, sir? You can please explain.
Yes, sir. The aliasing effect can be rectified with the help of the sampling criteria. So you have to maintain the sampling frequency should be greater than the maximum frequency available in the signal. So can you tell me that what's the maximum frequency of your signal?
If it is that a signal of the frequency 50 kilohertz,
50 kilohertz. Okay, sir. Then your sampling frequency should be greater than 1 megahertz. Sorry, 100 kilohertz.
okay, sir. Thank you.
Thank you.
Any other participants? Queries? Please use the chat box, otherwise unmute your audio and directly interact with our resource person. Dear participants, another one is having the chat box is the feedback form is posted in the chat box. Please complete the feedback form before 1:45. Up to 1:45 only it's enabled. Sir Sandil Kumar sir, thank you very much, sir, for your session is very nice and give for a lot of research scope to the participants. I hope all the participants are enjoyed these sessions. Thank you very much. Thank you, sir.
Thank you, sir. Thank you, sir. Thank you.
Thank you, Sandil Kumar sir. Okay. Participants, the next session will start on 3 p.m. today. We'll meet on 3 p.m. Thank you.